Hello, my name is Bruce Close, and my capstone project is titled Designing Low-Cost Virtualized Infrastructure for Hands-on IT Training. This project focuses on how schools, small organizations, and training programs can provide realistic hands-on IT training without needing a large physical lab, an enterprise cyber range, or a long-term cloud environment. The project is not about building a cybersecurity curriculum or a penetration testing guide. Instead, it covers the infrastructure needed to support safe, repeatable, and affordable hands-on technical training. Hands-on IT training requires an environment where students can actually practice. Reading about networking, operating systems, virtualization, or cybersecurity has its use, but practical skills are generally developed by configuring systems, troubleshooting problems, making mistakes, and going back and fixing those mistakes. The issue is that real production networks are not a safe place for that kind of practice. Students should not be experimenting with routing, firewall rules, vulnerable systems, or simulated attacks on the infrastructure that an organization depends on. Large organizations may solve this problem with dedicated physical labs, commercial cyber ranges, or cloud-hosted training environments. Smaller organizations often cannot. They may not have the budget, space, staffing, or support resources needed to maintain those systems. That creates the need for a practical alternative. A training lab for a small organization needs to be affordable, isolated from production systems, easy to deploy and reset, and realistic enough to support meaningful hands-on learning. The research question guiding this project was how can small organizations design low-cost virtualized infrastructure that supports safe, repeatable, and scalable hands-on IT training? The project used a design-based research methodology. That approach made sense because the purpose was not to run a live experiment, collect student survey data, or benchmark a deployed system. Instead, the goal was to use existing research, technical standards, and architectural analysis to design a practical infrastructure model. The process started by identifying the problem and defining the scope. Then I reviewed sources related to virtual computing labs, cloud-based lab environments, cyber ranges, network segmentation, virtualization security, and infrastructure as code. From the research, I identified the major design requirements for a low-cost training environment. The final output is an infrastructure blueprint and requirements model rather than a tested production system. The evaluation is analytical, meaning the proposed design is judged based on how well it addresses the requirements identified through the research. This slide shows the proposed infrastructure model. The design is local first, meaning routine training runs on organization-controlled hardware rather than being hosted entirely in the public cloud. The left side of the diagram shows the local virtualization server, which is the center of the design. The server hosts the lab virtual machines, virtual networking, firewall VM, access gateway, and monitoring tools. A firewall VM, such as pfSense or OpenSense, acts as the boundary between isolated networks and outside networks. Isolated virtual switches separate lab systems so that student activity does not directly touch production infrastructure. Golden images and snapshots make the lab repeatable. Instead of manually rebuilding systems, an administrator can create baseline virtual machines, clone them for students, and roll them back after each use. Apache Guacamole provides browser-based access, which lowers the requirements for student devices. Wazuh supports centralized logging and monitoring. The design also leaves room for hybrid readiness, allowing temporary cloud resources to be added if local capacity isn't enough for a larger class or event. This matrix summarizes the main infrastructure requirements identified through the research and connects each requirement to a design decision. Storage and compute sit at the foundation of the design. A classroom-sized virtual lab may have multiple students booting, resetting, or snapshotting virtual machines at the same time, so the environment needs a Type 1 hypervisor, sufficient memory and SSD or NVMe storage to support shared workloads without creating a poor user experience. Network security is just as important because the lab cannot be allowed to interfere with production systems. The model uses a dedicated management network, a firewall VM, isolated vSwitches, and controlled routing to keep student activity contained, even when labs include misconfigured services, vulnerable machines, or simulated attack activity. State management supports repeatability. Golden images, linked clones, snapshots, and rollback procedures allow instructors to create consistent lab environments and return systems to a known good state after each class or exercise. Administrative sustainability is handled through API access, scripted provisioning, and repeatable setup or teardown processes. These features reduce manual work and help prevent configuration drift, which matter for smaller organizations that may not have dedicated lab support staff. Access and usability are addressed through browser-based access with Guacamole. That lowers the requirements for student devices and supports users on Chromebooks, shared computers, or systems where they cannot install software themselves. Monitoring and assessment come from centralized logging and security event collection through Wazuh or a similar tool. This gives instructors visibility into system activity, student progress, and security events inside the lab. Scalability remains local first for routine classroom use, while hybrid readiness gives the organization a path to add temporary cloud capacity when local resources are not enough. Network isolation is one of the most important parts of the design. Virtualization alone does not make an environment secure. If a lab is poorly segmented, student activity could affect other students, shared services, or even the organization's production network. The proposed design separates management access and lab traffic. The hypervisor management interface should be kept on a restricted management network. Student lab systems should be connected to isolated virtual switches with no direct physical uplinks. When a lab system needs internet access or access to external resources, that traffic passes through the firewall VM. The firewall VM handles routing, filtering, NAT, and access control. That creates a boundary between the training environment and outside networks. This also makes the hypervisor a critical security boundary. If the virtualization layer is compromised, many guest systems could be affected. As a result, the design requires patching, administrative controls, restricted management access, and monitoring. Repeatability is another major requirement. Hands-on labs only work well if students can experiment freely and still return to a known baseline afterward. The proposed design uses a golden image lifecycle. An administrator creates baseline virtual machines such as Windows Server, Ubuntu Server, or Kali Linux. Once those systems are configured, they become templates. When a class starts, the hypervisor can create linked clones from those templates rather than copying a full virtual disk for each student. That saves storage space and speeds up deployment. Snapshots and rollback procedures allow the lab to be reset after use. If a student breaks a configuration, completes an exercise, or leaves the system in an unknown state, the environment can be restored without manually rebuilding everything. Automation also supports this process. Scripted deployment, template-based provisioning, and repeatable setup or teardown procedures reduce administrative workload and configuration errors. Access and monitoring are important because the lab must be usable, not just technically sound. Apache Guacamole provides clientless browser-based access to lab systems. Students can authenticate via a web portal and connect to assigned virtual machines using RDP or SSH right in the browser. That helps because students may be using Chromebooks, shared computers, or older laptops, or systems where they can't install software themselves. This supports the low-cost goal because the organization doesn't have to standardize or upgrade every student device before using the lab. Monitoring is also important. In a physical classroom, an instructor can walk around and see what students are doing. In a virtual environment, that visibility is greatly reduced. Wazuh, or a similar centralized logging platform, can collect logs, security events, and system activity from the lab virtual machines. That gives instructors better insight into student progress, system behavior, and security events during an exercise. The financial analysis compared a local first model against a public cloud alternative for a classroom-sized environment of 20 students. The local model used refurbished enterprise hardware and open source software. The cloud model used 20 virtual machines, each with 4 gigs of RAM, running about 40 hours per month with persistent storage. Under those assumptions, the local server baseline was approximately $2,200 in upfront hardware. The cloud alternative was approximately $3,048 in the first year and $9,144 over 3. That comparison suggests the local design may reach return on investment in less than one academic year for predictable classroom use. However, the baseline comparison is not the same as a complete total cost of ownership analysis. Electricity, cooling, labor support, maintenance, replacement parts, backups, security monitoring, and administrative time all matter. The local model can reduce recurring cloud expenses and licensing costs, but it still requires someone to patch the hypervisor, maintain firewall rules, update templates, monitor logs, manage backups, and support users. That means the model is cost effective only if the organization can also support the operational responsibilities that come with it. The design has several limitations. The first is that a single server model creates a single point of failure. If the server fails, the lab becomes unavailable until the hardware is repaired or replaced. Adding redundancy would reduce that risk, but it would also increase cost and complexity. The second limitation is finite scalability. A local server can support routine classroom use, but it cannot scale indefinitely. Hybrid readiness helps with temporary demand spikes, but cloud bursting adds cost and management complexity. The third limitation is expertise. The model reduces hardware and software costs, but it does not eliminate the need for technical knowledge. Someone still has to manage virtualization, networking, storage, templates, backups, monitoring, firewall rules, and security. Future work should move from design to implementation. A pilot deployment could measure CPU and memory usage, storage input-output performance, network latency, VM boot time, and snapshot rollback time. Future research could also measure student learning outcomes, perform a full total cost of ownership analysis, and test whether hybrid cloud bursting can be done securely and cost effectively. Overall, this project shows that smaller organizations can create realistic hands-on IT training infrastructure without needing an enterprise budget. By combining local virtualization, segmentation, templates, snapshots, browser-based access, monitoring, and selected cloud readiness, the proposed model provides a practical path for safe, repeatable, and manageable hands-on IT training.